Hey everyone.
Hello.
Hey, hello.
Who's ready to learn? We'll get started in about 10 minutes. We'll just give some people a chance to come in.
I'm going to try to rejoin with my camera here. I'll be right back.
Sure.
Hello, hello. Can you hear me? Hello. I'm putting my audio.
Hi. We can hear
Hi.
you perfect.
Hi. Thank you.
Hello everyone, good morning.
All right, guys, let's get started. Now, we are live on YouTube. We are live on Zoom. We are recording. Can everyone hear me okay?
Yeah, no problem.
Yes, perfect.
Yes, sir.
Awesome.
Yes, sir.
Thanks, Tippy. All right, let's get started. Let me move this stuff out of the way. Cool. So welcome everyone to the Smart Contract Developer Bootcamp. We have a few hundred people in the Zoom, and we've got a few hundred people in the live stream as well on YouTube. So whether you realize it or not, we're currently in the middle of a digital revolution. And when the internet first came around,
Can you mute
decades
everybody,
ago.
please?
Okay, sorry about that. How's that? Should be okay now. Now, when the internet first came around in the 90s, excuse me, and started to mature, there was a monumental shift in the way that people interacted with each other and businesses and how they operated and how we kind of interacted with each other. And it went on to change the way we do commerce, the way we do gaming and interacting with each other and socializing with each other and all of those things. Now, that was round one. The internet's coming again, this time round two, and this time it's going to fundamentally change the way in which we have agreements with each other and with businesses and entities, right? So smart contracts. Smart contracts are starting to gain real adoption in numerous areas such as DeFi, NFTs, insurance, gaming, art, and all of those things. And the adoption's continuing to rise and expanding to other areas as people start to realize the benefits that they have and how they can really take us into a new age of economic fairness, transparency, and efficiency. Now, we've got over 26 million developers worldwide today, but there's only a few 100,000 Solidity developers or smart contract developers. So we've got this huge up and coming industry, but then we've got this massive lack of talent as well. And learning smart contracts and Solidity isn't like learning a normal programming language. There's all these nuances and things involved. So that's why we've created this bootcamp as an initiative to help you guys begin your smart contract developer journey and to really just give you all the basics and fundamentals of smart contracts, Solidity, and as well as teaching you about what we call hybrid smart contracts that make use of Chainlink, which is a decentralized Oracle network. Because we feel that learning to use a decentralized Oracle network such as Chainlink is actually an integral part of a learning development path for a smart contract developer. And they enable you to really build the game-changing applications of tomorrow. And we want to teach this to you. We want you building the game-changing applications of tomorrow. We want you participating in hackathons, creating and joining startups, creating projects, doing all those types of things, right? We want you to be successful with smart contract development. So welcome to the Smart Contract Developer Bootcamp. We really appreciate you spending your weekend to learn with us. And we can't wait to teach you all things Chainlink, smart contracts, blockchain, and all of that cool stuff. So I'm excited, the team's excited, and hopefully you guys are excited. My name is Harry Papakarisiou, and I'm a developer advocate for Chainlink Labs. And there's my contact information there. And I'm joined today by some helpers. I've got Patrick and Zach from the Chainlink DevRel team. I've got Josh from Chainlink Labs as well. And we have a couple of helpers from the community today helping out. We've got Colin and we've got some members in the YouTube helping out with moderation as well. I think Scott, Kevin, and Juan. So say hello, guys.
Hey, everyone.
Hey, what's up, everyone?
I'm seeing a couple comments about audio. Everyone can hear me, right? Yep, cool. Okay, so here's the outline of what the bootcamp looks like. You guys are doing the weekend track. So we're trying to fit in a lot of stuff actually into just 2 days of a few hours each. So today we're going to focus on just teaching you some of the fundamentals, teaching about smart contracts, some basics in Solidity, doing some hands-on exercises in the Remix developer environment, deploying some contracts and just getting you familiar with some of those basics. And then tomorrow we're going to move on to some other development environments, and you're going to learn how to use them and learn how to interact with contracts with some of the more advanced developer environments. And by the end of it, hopefully you've got a good idea of smart contracts, a bit of practical hands-on experience with Solidity. You know how to use Chainlink to kind of make these awesome smart contracts that make use of external data, events, and computation and things like that. And yeah, hopefully it's just a really good starting point for your smart contract developer journey. So this course won't make you a smart contract developer professional, but it will give you a great starting point to then go on and continue with. So here's how it's going to work. Today's going to be a 3 to 4 hour session broken up into sections, and hopefully there'll be some little breaks in between as well. And the flow of how it will go is there'll be, I'll do some talking and presenting, and then we'll have some questions, and then I'll usually do a demo, and then we'll do an exercise after that, and then we'll kind of continue on. So if you have any questions, you can ask them at the end of each section. You can ask them, if you're in the Zoom call, you can ask them, you can chuck your camera and audio on and ask them, or you can just put them in the chat. Or if you're in YouTube, throw them in the chat. We've got people looking in there as well. And in the exercises, if you need help, if you're in the Zoom call, you raise your hand in Zoom, and one of our helpers will send you a private message in Zoom with a link, a URL, and you need to click on that URL, and it will open up a Google Meet session where you can have a one-on-one with a helper, and they can help you solve your issue. So keep an eye out for those private messages if you do have your hand up in Zoom. And if you're in YouTube, if you have any questions, ask them in the chat. We're constantly watching the chat during the exercises as well, and we'll try to help out when we can. If you solve an issue and you kind of see someone else ask about it in the chat, feel free to help them out as well. That'd be great. And if you get left behind in exercises, don't fret. We've got 5 exercises, I think, today. So when we get to the next exercise, you can always just continue on and try and catch up there. And at the end of the session today, we'll send you guys a feedback form. So it'd be great if we can get some feedback as well on today. So for today's exercises, in terms of the setup instruction that you guys got, we're only going to be working in Remix today. So you just need to have MetaMask installed, and you need to have some ETH and Link. And if you haven't done that yet, please do that now. And if you have some issues with the faucet, I know it's been a bit on and off lately, please post your Ethereum address in the chat, and hopefully we can sort you out there with some ETH or Link. So here's how today is going to look like. We're going to talk a bit about blockchain, smart contracts, Ethereum and Solidity. Then we'll talk a bit about Chainlink and some of the Chainlink tools and features. And in amongst all of that, we'll get some hands-on exercises done as well. So before we continue, I just want to say that we're going to go through some important concepts here because we want a really good foundation before we start to delve into the deeper things later in the bootcamp. And you can't become an awesome smart contract developer unless you have an idea of how it all works under the hood. So we also want to go over why you as a developer want to focus on smart contracts. So let's start with just a couple points on blockchain for those who may not know. So for those who don't know, or don't know much about it, a blockchain is basically just a network of computers all around the world that share data and transactions with each other, and there's a shared ledger that isn't controlled by any one person or computer. And the thing to focus on here is that they can actually run application code on them. You can think of them also as an application platform. So for example, Ethereum has a virtual machine to run simple programs on it. So just a very simple example here of 2 parties performing a financial transaction with each other. And the thing to note here is that the blockchain is decentralized. So it means no single person or entity can control or influence the behavior or the outcome of the transaction here. So in terms of decentralization and kind of what it means and how it kind of affects things, I like to think of it in terms of 3 different aspects. So architectural decentralization is how many physical computers is the system made up of? How many computers can the system tolerate breaking down at any one time? Political decentralization is how many individuals or organizations ultimately control the computers in the system, and does it is there like a large amount of people or companies that own large amounts of systems in the blockchain, or is there only a few? And logical is how does the system act? How does the system act if, for example, it's broken into 2? Do both individual pieces operate individually, or does the whole thing kind of get broken? So a blockchain is generally architecturally and politically decentralized, but not logically decentralized. So the benefits of decentralization, most of them are pretty obvious. So fault tolerance, less likely to fail accidentally because of the way they're architected. Attack resistance, they're more expensive to attack or destroy or manipulate because they lack these kind of central points to focus on attacking. And collusion resistance is much harder for participants in the decentralized system to act and collude in a way to benefit themselves at the detriment of others in the system. So let's just do a quick demo on this site, which is really cool. So I'm just going to go over a couple basic concepts here. So this is like an input text field here, and I'm basically putting in any kind of data. And hopefully that's big enough for you guys. And as you can see, this data is being hashed. So it's a cryptographic hash function. In this case it's a SHA-256. And as you can see, no matter what I put in, we're getting a hash, and the hash is always the same length. So, and one thing also to note is, if I put in the same thing in the data, it always ends up being the same hash. So a hash is one way. You can always come from one form of input to a hash each time, and it will be the same. But you can't take a hash and then work out what the data was. That's not how cryptography works. So that's kind of just demonstrating hashing data, because that's transactions and data is hashed on a blockchain. So let's now talk about a block. So here's just a very simple example of a block. We have a block number. We've got a nonce, which is pretty much just a number. Think of it as just a normal number. And data is kind of, you can imagine where transactions go in. In this case, we're just going to put in whatever. And as you can see, I have a hash here. So the whole block here is being hashed. So it's putting everything together and coming up with a hash. But as you can see, this block is like red, because the protocol for this blockchain basically says that this hash is invalid because it doesn't have the correct block difficulty in it. So in this case, we have a block difficulty of 4 because the protocol basically says the hash of a block needs to have 4 leading zeros right now. So, and if you noticed, when I press this mine button, this nonce actually changes to another number. So what the mining button is doing is it's finding the correct nonce values such that when you hash everything in the block, you get the correct number of leading zeros. So that's just a very basic example of what's called proof of work mining. So I think in Bitcoin, the block difficulty is 20, so you can't do that in a browser here. So let's talk about a blockchain now that we've talked about a block. So a blockchain is just a series of blocks all linked to each other. So I'm just going to make that a bit smaller. So I'm going to do the same thing with this first block, and I'm going to mine it. And we'll wait a little bit. And waiting. There we go. And I'm going to do the same thing here. Now, if you have a look here, there is a reference to the previous block hash in each block here. So the hash of this block is mentioned in the previous field here of block 2, and then the same for block 3. So every block is linked to each other. And in the first block, obviously, there's no previous block, so we get just all zeros. But the thing to note here is that because of the way that these blocks are linked, if you went and tried to change something in a previous block, i.e. change the past in the blockchain, you then change the hash of this block, which then breaks the link to the following block, which then breaks the link to the block after that, etc. So this is what gives blockchains this kind of immutable property, because it's not very easy to go back and change something in the blockchain, because you then have to mine not only that block, but then every block after that. And you need to do that faster than what all the participants in the blockchain that are not acting maliciously, you need to do that faster than them mining blocks that they are currently mining as well, which is kind of, very hard, or if not impossible to do, unless you control a majority of the network. So that's an example of a blockchain. So let's just talk about it in a distributed manner now. So let's say I've got a blockchain with just 3 blocks, and I mine the first one here, and it's thinking. There we go. And let's say I mine the first block. We have another peer here, peer B, and I'm going to mine a block with some other data here. And then in peer C, the third peer in this distributed network here, I'm going to put that in there. So what this is demonstrating is we're at the third block in the blockchain, and peer A says that the hash is this, 4F4B. Peer B says no, block 3 is actually this one, 7E9017 or whatever. And then peer C is saying, yep, I think this one is also this 4F4BD1. So in this case, what happens is it's this kind of little democracy, if you will, and basically peer A and B win because they have a majority vote over peer B, and then what they say block 3 should be ends up being block 3. So just a very simple example of demonstrating a blockchain. Hopefully that made sense for you guys. Do we have any questions on blockchain before we move on? Or Patrick, Zach, if there are any good questions in the chat, are there any we want to call out?
Yeah, just a quick note, actually. A lot of people are looking for ETH. Definitely follow along with what Harry's doing over here. I'm sending some people some ETH here. For those of you looking for Link, use that coven.chain.link instead of the protofire faucet there. So yeah, it has a lot of volume right now. So please be patient. Yeah, a lot of people are requesting right now, so it's having a hard time getting to everybody. But that's it. Yeah, any other questions? Welcome.
Adam asks, is the nonce only used to change the hash without changing the data? And that is totally correct. Yes, it's a way you can try to get that hash that you want without actually affecting the transaction data. So miners, they pick a nonce by like randomly, well, they increment usually up from 1 all the way up because their Coinbase transaction is unique. But yeah, they can randomly pick a random number each time or increment up from 1 either way.
Yeah, there's a lot of good questions. Oh, I love all these questions. Somebody in YouTube asked, what is a peer? So a peer is just anybody running a node, right? So when we're talking about peers, we're talking about nodes. You can run a node, I can run a node, anybody who's running a node. Yeah, so it's an individual.
We've got time for maybe just one more question, if you guys find any good ones.
There's a whole bunch in the chat here.
Yeah, there's so many.
Not sure. Understand what is mine. Oh, no, that's Jonathan responding. Sorry. Is the hash value always unique, or could two inputs into the shade 256 generate an identical hash value? So this is actually this is a really good question. So there's something called what is it called? Collision rules. That's not what it's called. I actually have to I gotta look into what it's called again. But yeah, they're basic collision rules for if you generate a hash and that already exists. Basically, there's a rule that says, okay, we're going to change it a little bit, but I have to go and double check. Yes, everything should be unique though.
Cool. All right, let's move on for now. Cool. So let's talk about smart contracts now. So a contract. What's a contract first? So it's just a binding agreement between two or more parties, and these kind of things started out a long time ago, written on stone and paper and things like that. But as time moved on, obviously now they're all done digitally now on computers. So they're what we call digital agreements. So that the storing and executing of the agreement is done digitally now. And a lot of people may not realize this, but these digital agreements actually underpin a large aspects of our lives today. So we all have digital agreements with our bank that says, hey, I'll store your money and I'll give you, X% savings rate on your savings. We have agreements. You might have an agreement with Netflix to say, hey, you pay, $15 a month or whatever it is, and you can access our streaming content. You have an agreement with your insurance company that says, if your car gets stolen, I'll pay you, this much. So various examples of digital agreements. And there's one thing I'd like to point out with a lot of these digital agreements, and that's that one of the parties in the agreement itself is actually the party that's actually enforcing and executing the agreement and actually determining the outcome of the agreement as well. So one of the parties in the agreement is kind of the one that's in charge and is basically the one that says, all right, this is what's happening. So because of this, these agreements can kind of be thought of as high risk in some cases, in many cases, and low control for the general user. And they can kind of be thought of as a bad deal, basically. And they're built to favor specific actors, right? Because they're the ones that are in control in the end. So they're what we call a paper-based guarantee or a brand-based guarantee. They're saying, trust my brand. And these contracts are foundationally built on law, obviously, as well. But the law doesn't always help you because they word these agreements specifically in a way where if they need to, they can kind of screw you over, basically. So they're saying, trust in my brands, trust in my, reputation. So one good example of this is the traditional financial system and how it's skewed to benefit certain better informed, better resource actors. And everything works well in normal market conditions when the people that are meant to be making money are making money and everything's working as it should. But then when certain conditions occur, when these people are not making money and things aren't going as expected for them, that's when we kind of find out how these digital agreements really work. And in many cases, what actually happens is these systems stop, or the agreements are executed in a way that's often detrimental to the general user and to the benefit of these kind of institutions. So we've seen countless examples of this happen over the years. The Robinhood GameStop fiasco from earlier this year is a great example of that. The people trying to buy GameStop on Robinhood, they had a digital agreement with Robinhood, which Robinhood then, negged on. Going back a few years, the Greek banks locked up ATMs and people were only able to access 66 euros per day. I was there in Greece at the time and I saw that. A few years before that, the Cyprian banks took between 6 and 10% of everyone's deposits in the bank because they needed it for some bailout negotiation. So people just had their money taken away. Even more recently, I had a family member trying to buy crypto assets here in Australia, and it was their first time and they needed help and they don't do internet banking, and they had to go into the bank and the bank wouldn't transfer money to the most legitimate and reputable crypto exchange in Australia because they found out it was for crypto. And this person said to them, who are you to say what I do with my money? Like, you can't stop me from sending money if it's to a legitimate business that's registered with all the relevant authorities and things like that. So yeah, just want to reiterate that these agreements are foundationally built on brand-based trust. So these types of things are going to continue to happen and kind of continue to create a crisis of trust. So a bit over a decade ago, along came Bitcoin, and then a few years after that, Ethereum, and all of a sudden we've got smart contracts. So smart contracts are not really smart and they're not really a contract either. So I like to think of them more as a highly secure, tamper-proof digital agreement. So the difference between a traditional digital agreement and a smart contract is that these smart contracts run on these blockchains, which are decentralized infrastructure. And they enable us to rethink and change the way in which we execute and enforce these agreements, because in a smart contract scenario, the contract execution and enforcement is done by this completely separate thing that's got nothing to do with the participants in the agreement, as opposed to a digital agreement where one of the parties is usually the one that's in charge of kind of doing that thing. So it's a huge shift because we've got this completely separate thing that can't be hacked, gamed, manipulated, bribed, blackmailed, or anything. It's got nothing to do with politics, and it will just execute things exactly as they were coded. So why is a smart contract better? It basically boils down to 5 things. So the first one is security. So because it's running on this decentralized infrastructure, like I explained just earlier, they're very hard to hack, manipulate, or influence. Second, reliable, guaranteed execution. Once again, due to the unique properties of a blockchain, your smart contracts are always going to execute as programmed, and there's never going to be a scenario where they won't execute as long as you can basically pay for transaction fees and things like that. So it's not like Visa or MasterCard or anything where payment processes may sometimes go down. That a blockchain doesn't go down. Well, a good one doesn't anyway, unless there's a worldwide power outage or internet outage or both. 3, transparency. So usually with traditional digital agreements, transparency is usually very low, and certain information is usually withheld from participants in these agreements. Whereas in a blockchain scenario with smart contracts, transparency is unavoidably built in. So 4, trust minimization. Because we are running these smart contracts on this completely unhackable, ungameable third-party thing that no one can influence, we don't need to trust the people that we have these digital agreements with as much, because we're trusting in smart contracts and blockchain to kind of act in the way they do. We're trusting in maths and cryptography instead of brand and vague promises and things like that. And 5, efficiency. So all of these things that I've discussed, security, guaranteed execution, transparency, etc., they provide an opportunity to kind of take some of our existing processes and migrate them to be better, more efficient, because in the end, things like security, trust minimization, those are expensive things to do, right? So just to kind of close off smart contracts, when you're comparing these traditional paper or brand-based digital agreements with smart contracts or these math-based agreements, they're completely opposite in terms of the counterparty risk and transparency. So basically, these smart contracts are low counterparty risk and built-in transparency. And you might take a look at this and say, well, that all makes sense, but I can't see some of these companies and organizations giving up control and kind of executing their agreements on these things that they can't control themselves. And it's a valid point, but I think history has shown that the best user experience and best user experience generally ends up winning in the end once it can kind of be implemented at scale and at a decent cost. And there's some examples of this that kind of demonstrate that point, such as going to streaming services for video and music. So the music and movie industry didn't want that, obviously. Software as a service, 20 or so years ago, people used to say, no, I'm not going to put my data on some program on the internet. I'm not going to put my financial data and customer data. Obviously today, everyone puts their data on the cloud and on these software as a service platforms, including their most valuable data, such as customer and financial data. So there's some countless examples that kind of demonstrate this. Any questions on smart contracts? Sorry, I forgot to share the result of the poll for those in the Zoom. So just a little trivia question. What was the original term for blockchain as outlined in the first version of the Bitcoin source code? The answer to that is time chain.
Got an interesting question from David here. In terms of solidity and blockchain use, how confident are you that this knowledge is actually going to be useful for me in the future of the world? Crypto world appears to be under a lot of scrutiny from governments. Is this knowledge actually worth pursuing given the pressure basically that's going on in the world? Absolutely, 100%. So something really interesting is that Ethereum and Bitcoin right now are, according to the SEC, commodities. So they're not securities, so there's no pressure on them. Basically, the government considers them exactly the same as like wheat or corn or oil, right? The exact same type of substance. So given that this is literally, kind of the same as stuff you can find outside, right? Like they have kind of the same governmental scrutiny there. And given the power that they have, that Harry was just kind of going over with these superior digital agreements, the answer is absolutely, positively, 1,007% yes. And I actually thought you were going a different way with this question when I initially read it. I thought you were saying, "Oh, well, is it going to be different in 5 years?" No, all these fundamentals are still going to be the same. Hashing is still going to be the same. Hash algorithms are still going to be the same. All these core concepts are going to be the same, and this will absolutely 100% be useful in the future. And given what Harry's saying here, it's just a better way to go about our lives and live in a world where we don't have to trust and we don't have to deal with this counterparty risk. So absolutely.
Nice one. The next trivia question I posted on smart contracts: who originally came up with the concept of smart contracts? The answer to that is Nick Gazebo. Back in the 90s, I believe.
Tricked you guys.
Okay, I think we're a tiny bit behind schedule, so I might just move on now. So let's go on to Ethereum and Solidity next. So Ethereum, for those who don't know, it's a public or permissionless blockchain. So that means anyone can use it, and it's open source, which means that the code is out there for anyone to have a look and verify. And it's got a native cryptocurrency called ETH or Ether, and you can kind of think of it as a transaction-based state machine, which means it transitions to a new state, every time basically a block is mined. So it currently uses proof of work as its consensus mechanism, but it's in the process of transitioning to proof of stake. So the main concepts for Ethereum to kind of get your head around, if you don't know these already, there's a bunch of nodes obviously in Ethereum. I think there's about 15,000 or something total, or last time I checked anyway. It's probably more by now. And there's accounts, so wallet accounts or addresses, and there are transactions as well. So each time a block is mined, we have a number of transactions. And there are also what we call pending transactions, or the mempool, which contains all of the transactions that have been sent to Ethereum but haven't been included in a block yet. So they're still kind of pending to be included. So Ethereum has what's called the Ethereum virtual machine as well. So you can basically think of it as a virtual machine to execute smart contracts, and it's built into the protocol itself, and it determines the outcome of the executed smart contract logic. So all the nodes running the Ethereum software, all the protocol execute the smart contract code. That gives us our kind of hyper redundancy and hyper security. So yeah, the Ethereum smart contracts are executed in the EVM, and we program the smart contracts in a language such as Solidity. There's others as well, such as Viper, but Solidity is the most popular one. And these contracts are then compiled into what's called EVM bytecode, which is then sent to the EVM when you kind of deploy the smart contract and you want to execute it. So yeah, once again, ETH or Ether is a native cryptocurrency of the Ethereum network, and we use it for transaction fees and computation. So you've probably heard of the concept of a token before, so I won't spend too much time. It's basically a representation of any tradable good or service or unit of account, and there's some use cases there. Most of them are defined as what's called the ERC20 token standard, but the Chainlink token is actually an ERC20 with some extra functionality built on it, and it's an ERC677. And that extra functionality is basically you can send a token and call a smart contract function all within one transaction, whereas with an ERC20 token, you need to do that in two separate transactions. So just one thing to take away here is that a token is not like the native cryptocurrency Ethereum in this case. A token is literally a smart contract on Ethereum that has a bunch of wallet addresses and it says who's got what. And then every time you transfer a token, it then updates that that basically list of who's got what basically. So it's just a smart contract. So Solidity is the main programming language for creating smart contracts on Ethereum and lots of other EVM based chains as well, actually. So it's very similar to JavaScript or C# for those who kind of know that. And it has inheritance, such as, object-oriented programming and libraries and all of those types of things. So the argument for having its own programming language was because many compilers with existing languages aren't optimized for storage. And because we have, literally thousands of nodes around the world running this protocol and kind of storing this data, we kind of need to focus on keeping things as lean as possible. So there was a focus on storage, and also being a blockchain, there was a big focus on security as well, which a lot of other languages and compilers don't focus on enough, or the creators of Ethereum didn't believe so anyway. So when you compile your Solidity code, you actually get two things as an output. You get what's called the bytecode, which is the EVM instructions for your smart contract. And then you get what's called the ABI as well. So the ABI is the application binary interface. And it's basically a set of JSON, as you can see in the example here, a JSON string that basically has all of the information needed to interact with the contract. So it says, what are all the methods that can be called? What are their inputs? What do they return? What are the events? So any other computer program or process or contract or anything, given a smart contract address, they can take this ABI and they can know how to interact with that contract. So the contract, once compiled and deployed, is published to the blockchain, the bytecode is, sorry. And then to access that contract, you need to have this ABI definition to know what the inputs and outputs are and how to interact with that smart contract. And you'll see an example of this in the first exercise. So gas, let's talk about gas. So gas is used to execute smart contract functions because executing smart contract functions is not always free. So gas is the internal unit for keeping track of the execution cost of a smart contract function call. And it's split into two things, gas cost and gas price. So gas cost is always kind of static. So doing the same thing multiple times will always have the same gas cost, such as writing 32 bytes into a smart contract is always going to cost you the same in gas cost. Gas price is how much you're willing to pay for that gas cost. So you can think of gas costs as driving from one town to another. You're always going to approximately need the same amount of gas in your car, like 20 gallons, whatever it is, I don't know. Whereas gas cost is how much you're willing to pay for that 20 gallons that you need, basically. So that's kind of a good analogy to compare the two. So the gas price can be negotiated, but it must always be greater than zero. And we'll go into some of those kind of scenarios in a little bit. So every time you execute a contract function, gas is measured and paid for. If you're just reading data from the blockchain or from a contract, it's free. You don't have to pay any gas. And the gas price is set by you or whatever the process is that's kind of executing the smart contract function. And obviously, the lower the price, the more time it could take for a miner to include that transaction in a block, because they'll generally focus on transactions with the higher gas fees. So there is also a gas limit on transactions. Because we have a blockchain where it's running on thousands of nodes everywhere, we can't have smart contract functions like just constantly running, because that would just, the blockchain would grind to a halt then. So there's actually a limit that you set when you execute a transaction. And if the limit is reached, the contract execution actually stops, and any changes to the contract state will revert or undo, and you'll kind of, you lose the ETH that you spent on that gas. So an Ethereum block is mined every 15 seconds, give or take. And it used to be 12.5, but now each block has a 15 million gas limit. So there's not a transaction there's not a set amount of transactions per block. It's calculated in gas. So that roughly equates to approximately 200 transactions per block, give or take, depending on what the transactions contain. So just to reiterate, anything that's not changing the blockchain, that's just reading from the blockchain, is free. You don't need to spend any ETH in the form of gas. Anything that is changing the blockchain, writing to smart contract memory, sending ETH, sending tokens, executing smart contract logic, that you need to spend gas. Okay, so let's talk about what happens when Ethereum has transactions sitting in the mempool or the unprocessed transactions area. So a good way to kind of explain this is what I call the bus analogy. So when you catch a bus and you go to the bus stop, there might be a line there, and if there's a few people, you wait in line, and when the bus comes, you wait, and the first person in the line gets on first, and then when you get to the bus, you pay your fee and you get on the bus as well. So with blockchains and Ethereum, it's not like that. It's a little bit different. So you can think of the bus as the next block that's going to be mined, and you can think of the bus driver as the miner. So he's the one that decides who's going to be on the next block or which transactions. And the people at the bus stop, they're the transactions wanting to get on the bus or onto that next block, if you will. So it's not a first come, first serve scenario like in the normal bus analogy. The miner will actually look at all of the transactions and see which ones is going to make them the miner the most money, basically. So this is generally what happens, not all of the time, and there's some other cases such as MEV and things which we won't go into today, but for the purposes of this intro course, we'll say that's what generally happens. So let's say the bus can fit 100 people and there's 80 people at the bus stop, then things are usually pretty smooth and everyone generally pays a normal fee to get on the bus. But let's say there's 200 people waiting at the bus stop and only 100 people can get on. That's when it gets interesting, because the miner or the bus driver is obviously going to pick the 100 people with the highest, willing to pay the highest fee. And because everyone knows that there's 200 people in the line, they know that if they want to get on, they have to offer more than kind of like a standard price or transaction fee. So it becomes this kind of bidding war where the transaction fee to get your transaction mined in the next block gets to a much higher level, because everyone's kind of offering these inflated prices to try and get on. And if you don't offer an inflated price and you keep it to what you consider a normal price, you run the risk of not being chosen in that lot of 100 people. And you also run the risk of when the next bus comes around or the next block is waiting to be mined, if there's more than 100 people, then you can get left out again if you don't raise the amount you're willing to be paid. And that will continue up until when the blockchain is not as congested and when there's less than 100 people in this scenario, basically. So that's kind of just a neat little analogy to explain what happens when there's a high number of transactions waiting to be processed. Okay, so let's talk about contracts and functions. So contracts in Solidity, very similar to classes in normal programming languages, and functions are basically just executable lines of code within a contract, and once defined, they can be invoked with arguments. So function visibility, very similar to other languages, public versus private, anyone can call them, accessible in the contract only. And then we also have external and internal. So external is similar to public, but it's only for things external to the contract. And I think it's slightly cheaper execution cost than public as well. And internal can be called from within the current contract or contracts deriving from that contract, whereas private is not accessible from derived contracts. So here's just a couple of examples of functions with parameters and also return values. So the first example here is we have a function called store, and it takes one parameter, which is an unsigned integer, and we call it num, and this is a public function, so anyone can call the function. And in this example, we're just storing the variable the parameter that's come in, we're just storing it in our smart contract into this number variable here. And the second example here, we have a function called retrieve. This has no input parameters. It is once again a public function, so anyone can call it. In this case, we're also specifying the view reserved keyword here. So this basically says that this function is not modifying the state of the blockchain. You don't need to go and charge the person gas for it, or they don't need to pay gas because we're just reading stuff. That's basically what that means. And in this case, we're returning an unsigned integer in this function. And as you can see, we're just returning the number variable there. Just a couple very simple examples. So data types in Solidity, very similar to some other languages as well. So we have integers and unsigned integers, but we've got no floating point numbers here, guys. It's only whole numbers only, no decimal points. You can't do decimal points or floating point numbers in Solidity. We've got Booleans, true or false, strings and byte strings or byte arrays. And also we have Ethereum addresses, which are 40 character hex encoded character strings with a checksum. And finally, we've got what are called enumerated types, which are basically just custom user defined types. And there's a good example of one down the bottom there. So arrays can be done in Solidity as well, very similar to other programming languages. You can have them as fixed size at compile time or dynamic, and they can hold arbitrary types. And we can also call a couple members to find out, how big is the array, and to add things to an array. So there's a couple examples there. Here is a fixed size array, so we're defining it here. We want to hold 3 values in there, and that's kind of an example there. And here's an example of a dynamic array where we're defining it here without specifying a size, if you will. And then we've got a function here which basically just pushes an input variable here onto the array. So Solidity can do mappings as well. So a mapping is basically just a key value pair. So a way to think of it is similar to how your phone stores phone numbers, and you can kind of look up someone's phone number by entering their name in your phone book. So just you have a key and then there's a value. So mapping is the same thing and allows smart contracts to easily retrieve data based on a key. And the key isn't actually stored on chain in this case. Its hash is used to look up the value. So there's an example here of a mapping of a string to addresses, and we're saying in this mapping we're saying Harry's account or address is this one here. So structs, you can do structs in Solidity as well. A struct is basically just a collection of primitive types where you're putting them together and then calling it something. There are some restrictions on them that I've listed there, and there's a good example at the bottom where we're creating a struct called account, and it contains an address and an integer, and it's just an example of creating one there. Cool, so we're actually at our first exercise now. I thought what we might do for this one is we'll try and do this one together. So Zach or Josh, whoever, can we share the exercise links in the Zoom and YouTube, and we'll try and do this first one together. So I'm going to go into my remix. I'll give you guys just a couple seconds to open the exercise up. If anyone has any questions on the slides that we've gone through just the last few minutes, feel free to ask now. Cool. All right, has everyone got the exercises open, and does everyone have Remix open? Cool. So for those who haven't been here before or been to Remix, this is kind of what Remix looks like. It's an online developer environment for Solidity and for creating Solidity smart contracts. It's very easy to use. It's all kind of point and click graphical user interface, and it's a really good starting point for someone just getting into the space. So The first thing you'll notice is there's a workspaces area on the left here. You should have a default workspace created. If not, you can create one with that button there. Can we paste the link to Remix in the chat, guys? I think if you've got the exercise open, it should be as literally the first thing for exercise 1. So you should see the link there. So this is basically just an explorer for kind of going through any contracts you've created, and there's some links to create new ones. And there's like an output or terminal thing down the bottom here where you can see transactions being executed, etc. And there's an explorer window, a code window here. So in terms of these tabs here on the left, the things that we want to focus on is this first one just always goes to your files here that you have open, or your contracts. The second one is the Solidity compiler. So this is where we go when we want to compile our smart contracts. And the third one here with a little Ethereum logo is the deploy and run transactions section, where we go to obviously deploy and run our smart contracts. So the first thing that I want us to do is create a new smart contract by pressing this button here and call it my first smart contract. And if you hit enter, it should open it up in the code window here. If you've got 2 monitors, it's a good idea to put Remix in one and the stream on the other. If you don't have 2 monitors, then hopefully you're good at switching between the 2. So I'll give you guys just a few seconds to get that smart contract created, and then we'll start putting some stuff in it. And if you've got 3 monitors, then you're elite. Okay, so the first thing we're going to put in our smart contract is there we go. The first thing we're going to put in our smart contract is this pragma statement. And what this is doing is it's telling the Solidity compiler, it's saying, hey, we want to compile this on any version of the compiler that's 0.67 or greater up until, and I think this little thing here means that it can go anything up until version 0.7, I think. So because if you go to the compiler tab here, you can see there's a whole bunch of different versions of the Ethereum compiler. They're always constantly releasing new versions, new features, etc. So this is a way where you can kind of make sure that your code won't not compile because someone's using a different compiler than what you want them to. So now that that's done, hopefully you guys have put that in. So all we're literally going to do now is we're going to create a new smart contract by saying contract my first contract, and you put your curly brackets, and that's it's kind of like defining your class basically, but in this case we're defining a new contract and we're calling it my first smart contract. So I'll give you guys a few seconds to put that one in. Okay, hopefully that's been enough time for you guys to create that. So the next thing we're going to do is we're just going to create a new variable, which is an unsigned integer. You could specify uint 256 if you want, but you don't have to. I think the default is a 256 bit, and we can call it number in this case. So we're literally just creating a new variable. It's an unsigned integer, and we're calling it number. So once that's done, we're going to create a new function with the function keyword. And we're going to call it change number. And in the input parameters, we're going to say it's taking a unsigned integer input parameter, and we're going to call it num. And we put our curly brackets. So we're saying, okay, this contract has a function. It's called change number, and it takes a uint256, a parameter called num. For those who asked why the underscore, that's just a, it's not a standard, but it's just more of a thing that people do with input parameters. They kind of prefix them with an underscore so that when you're dealing with the code and you're kind of working with variables in the contract and input variables to the function, you can kind of know which one's which. So in this function, all we're literally doing is we're assigning the num variable to the number one in our smart contract. So very simple function. It just literally sets a variable in our smart contract. And as I defined before, whoops, sorry, I forgot to put public here too. So it's a public function, anyone can call it, and it's literally taking in a number and storing it in our smart contract. Very simple. If you want to write comments in Solidity, you do 2 forward slashes, and then you can put whatever you want if it's on a single line. So for those who may not know, a comment is just lines in a Solidity contract which the compiler will ignore, and it's there for human purposes only. If you want to do it across multiple lines, you do /*, then your comment, and then */. So let's create a second function now, and we're going to call this one get number, and this one is also a public function, and this one is a view function because we're not changing the state of the blockchain here. And in this case, we're going to return an unsigned integer 256, and whoops, my mouse is gone. And all we're doing is we're returning the number variable. So yeah, for those in the comments, it's very much similar to like a getter and setter example that we've got going here, just to demonstrate some of the syntax and demonstrate changing the state of a smart contract. So I'll give you guys just a few seconds to complete that. Thanks for the tip on the misspelling, guys. Typing with my microphone in the way isn't always easy. So once you've done that, you can click on the Solidity compiler tab, and there's this blue compile button down here. So you literally just press that button. You can ignore the warning for now. Don't worry about that. If it's an error that's red, then worry about it and kind of try and work out the issue or ask about it. But if it's orange for now, a warning, just ignore it. So the view function, like I said earlier, specifies that this the view modifier, it just specifies that this function is not modifying the state of the blockchain. It's just a view function, so whoever calls it can just call it and they'll get a response straight away, and they don't need to pay any gas. You'll notice that if I actually modify the state of the contract and had the view reserved word here, if I then tried to compile it, then you'll find that we actually get this kind of error here that says function declared as view, but this expression potentially modifies the state and thus requires non-payable or something. So let's get rid of that. So once it's compiled, we're now ready to deploy our smart contract. So the first thing that we're going to do is we're not going to deploy it to a real Ethereum network yet. So if you click on the deploy and run transactions tab, in the environment drop down up here, there's 2 JavaScript VMs, and you can just choose one of them, any one of them, it doesn't mind. And it doesn't matter, sorry. And what this is it's just a, it's kind of like simulating an Ethereum node running in your browser. So everything happens directly on your computer. There's no Ethereum network. And we do this to start off with because everything's fast. We don't have to wait for blocks to be mined. We don't need real ether, and it's good to just kind of play around with things. So just once you've compiled your contract, change your environment to JavaScript VM, and there's a orange deploy button here. But before you press it, and I get caught out with this all the time, make sure your contract drop down here has the correct contract. In this case, it's all fine. And you hit the deploy button. So I'll give you guys just a few seconds to catch up there. If you're getting an error about your compiler version, make sure that the version you specify in your pragma statement here, it's better just to match it at least over here. So in this case, mine's compatible 6.12, it's within the range, but if you put 0.67, just pick 0.67 in this drop down here. So once you've deployed your smart contract, you should see in the bottom corner here, there's a deployed contracts section, and your smart contract's listed here, and you can literally press the copy button to copy the address, and you can kind of expand, press this little arrow to expand it. And what you can see is we've got some buttons here. We've got a change number button and a get number button. And what Remix has done is it's taken the ABI, which I talked about earlier, from our compiled smart contract, and it's generated these little buttons, this little graphical user interface, so that we can then interact with the contract based on the ABI. And you can actually even look at the ABI by going to the compiler tab, and after you compile it, you can actually, there's some buttons here for the ABI and the bytecode. So if I just copy the ABI and in fact, you know what? It's probably easier if I just do this. So here you can see our compiled ABI here. It's got our 2 functions, the inputs and outputs and all of that stuff. So that's kind of how Remix generates these things. So now all you need to do is we'll put in a number and we'll call change number by pressing the button. And you can see in the output down here, it was successful. And then if you call the get number, we get our number return that we passed in the change number thing. So I'll give you guys just a minute to play around with that and get that running successfully. And then we'll try it on the Ethereum Coven network next. So we're deploying and executing this just on our local computer in our browser. So that's why it's all very quick. And when we haven't had to interact with our MetaMask wallet or anything like that. So just to quickly repeat the compile and deploy process, on the compile tab, I'm hitting compile, and you should have the complete contract code source in the exercise too. And then once it's compiled, I'm going to the deploy and run tab. I'm making sure environment is set to JavaScript VM, any of the 2. And I'm pressing the deploy button. And then once deployed, I'm looking at my deployed contracts section in the bottom left here, and I'm executing the functions by literally putting in the input and then pressing the button. So yeah, you can put any number in and you'll get a response. You should get it because you're storing it in the smart contract. So hopefully you guys have had enough time to get that done. What we're going to do now is we're going to do exactly the same thing that we did with the same contract, but we're going to do it on a real network. So this is where you need your MetaMask, and you need some ETH in your MetaMask as well. So in the deploy and run transactions tab, in the environment dropdown, I want you guys to change it to injected Web3. And this is where it should connect to your MetaMask wallet. If it doesn't, you may need to click on your MetaMask little fox icon, and you may need to hit a connect button here. I don't have to do it for mine, but you may need to. So hopefully you get that connection to your MetaMask wallet going. If you don't, definitely ask in the chat and we'll try and sort it out. So once you change the drop down to injected Web3, this is basically saying, all right, we've got our compiled smart contract, but we actually want to deploy it on an actual proper network. Now, in this case, on our MetaMask, where you should be connected to the Coven test network here. So make sure this drop down here, is also set to the Coven test network. And you should see some text underneath here that says Coven network or network 42. That's Coven. So we're saying, all right, we want to deploy this to Coven now, which is a real Ethereum network. It's got lots of nodes, not as many as the mainnet. This is like a test network for doing testing and kind of playing around with smart contracts. But it has real Ether, and it's a real decentralized Ethereum network. And once you've done that, press the deploy button again. And this time you should get a pop-up from your MetaMask wallet that says, hey, I got a transaction here that you're trying to do. I see you want to deploy a new smart contract. Here is the gas fee that I think you need to pay to get this done in a normal amount of time. And all you have to do is you just leave everything as default values and just hit the confirm button. And then you need to wait a few seconds. So I'll just give you guys a few seconds to do that deployment. Once again, make sure your MetaMask is on the Coven test network here. So there's a drop down right at the top of MetaMask that you can press on, and you should have at least 3 or 4 or 5 options, and make sure you have Coven test network selected. And to the left of your main wallet address or name, there should be a green connected icon. If it says connect and it's not green, press on it, and hopefully you can kind of get it connected to Remix. So the combination of having your MetaMask set to Coven test network and then having your deploy and run transactions drop down here at the top, the environment set to injected Web3, that should kind of get you connected. If you can't get a connection, try refreshing your page in Remix. You won't lose your code. It stores everything in the browser cache. And then just try change the environment to injected Web3 again. If your transaction's still pending, it may be because there's like a few hundred people trying to deploy a smart contract now. But hopefully they will go through soon. So once that's done, just like before, you should be able to do exactly the same thing. You should have a deployed contract in your deployed contracts section here with a change number and a get number button. If you call get number, it's going to have nothing in it. It will show 0. If you call change number, it's going to be similar to last time, except you're going to get a MetaMask pop up again, because once again, you're trying to execute a function that's going to change the state of the blockchain. So you need to sign the transaction, you need to confirm it. So you just leave everything as default values that kind of says, all right, this is the gas fee that you probably need to pay. You say confirm, and then you wait for that transaction to be confirmed. And then once again, if you hit get number, you should be able to see a result. So I'll let you guys play around with that for about a minute, but just quickly, I'll show you as well. If you copy the smart contract address here using this button, you can then go to the coven.etherscan.io website and paste in your contract address and search for it. And you can actually see all the transactions for your smart contract here. So you can see there was 2 transactions here. The transaction to create the smart contract, and then another smart contract to, another transaction to call the change number function. And you can kind of go into each transaction. You can kind of see what the transaction fee was, what the gas price was, and all of those cool things. So I'll leave that with you guys for about a minute or so to try and get that going. And if you have any issues, paste them in the chat and we'll try and help you out. And yeah, the creation of the contract isn't 0 ETH. It's just, it was, quite low. So now we're just getting the same smart contract, but instead of running it on our local computer in a browser, kind of simulating Ethereum, we're deploying it to the actual Ethereum test network, and we're interacting with it on the live Ethereum test network, and we're paying ETH in the as a transaction fee to basically deploy it and interact with it. We'll give you guys another minute or so to play around. So for the person who asked, where is Etherscan getting the change number thing from that we saw here? It's actually getting it from the contract ABI, I believe, which I showed you guys before. Cool. Okay. Hopefully, most of you are able to get your smart contract deployed on Coven successfully and interact with it. Where are we? Here we are. So yeah, we're going to move on, but we're going to go pretty much straight into the next exercise. So don't fret if you're a little bit behind. But for those who were successful, just want to say congratulations, guys. For those who have never done this before, you actually deployed your first smart contract onto a real Ethereum network, and you did your first interaction with a smart contract. So huge congratulations. It's a huge step into your journey as a smart contract developer. So congrats to all.
Nice work, guys. Yes. Excellent. You guys are one step closer. Deployed your first smart contracts. Yes. Thank you, Harry.
But now we're gonna actually play around with that smart contract and add a couple of other things to it. Wow, some people did the bonus, congrats. So in that last exercise, we created a very simple smart contract. We deployed it to a local network, or a local kind of simulated Ethereum network. And then we deployed it to Kovan, and we interacted with it as well. So what we're going to do now is we're going to add to the smart contract, and we're going to add a couple of things to it as part of the second exercise. So this one we won't do it together, but I'll just kind of put the code in and run it through with you guys just quickly for a few minutes, and then I'll actually let you guys do it yourselves and give you a decent amount of time to do it yourselves after. So if you just want to kind of focus on me just for a couple of minutes and what I'm talking about, just so that you kind of get the concepts, and then you can kind of go and try and do it yourselves. So we're actually going to add an array to this smart contract. An array, as you remember, I discussed arrays briefly before. So in this case, we're adding a new array of strings, and we're calling it names. And then we're adding a function to add basically strings to the array. It's a dynamic array. And in this case, we're taking in a name string, and then we're just pushing that onto the array of strings there. So some people ask, what is the memory? Special word there? So basically, memory is basically telling the smart contract that we want to store this string in the temporary memory of the Ethereum or the EVM or whatever's executing the smart contract. We don't want to store it in the persistent storage. So there's certain things where after certain compiler versions in Solidity, there's certain things such as strings and arrays where if you have them as input parameters, you actually need to specify whether you want to store those parameters in just the temporary storage area that just is in memory just for the duration of the function execution, or if you want to actually store them in the smart contract permanently. So there's certain cases where you might want one way or the other, but in this case, we just want to store this name variable for the duration of this function execution. So we say memory. So all we're doing is we're adding the name string to our names array. And likewise, we have another function called getName that takes an index, an integer, and this is another public function, and it's a view function, so it doesn't modify the state of the chain. And in this case, we're returning a string, and once again, we just want to store it in the temporary memory for when we're executing this function. And all it's doing is it's returning the value in the array at the specified index. So once again, very simple, kind of like a getter and a setter. This time it's with an array, and we can add as many things as we want to the array. So I'm just going to make this a bit smaller. No, that's not good. So I'm going to compile this contract just like we did before, and just for the purposes of this demo, I'm just going to do it on the local JavaScript VM because it's quicker. So I'm going to go deploy just like we did before. We have a new version of my first smart contract deployed down here. So I'm going to add a name here. So Alice. And that's successful. And I'm going to add one more, and Bob. Successful. And then if I call getName passing in the index of 0, I get Alice, and then if I call getName passing in an index of 1, I get Bob. So just a simple demonstration of creating an array in your smart contract, adding strings to your array, and then grabbing or retrieving elements from your array. So just a very simple exercise with arrays there. So that's arrays. The second thing we're going to add to the smart contract here is we're going to add a mapping. Whoops. So in this case, we're going to add a mapping, and we're going to call it phone numbers. And this mapping is a mapping of strings to integers. So kind of like a phone index or something in your mobile. And just like our last example, we're going to have two functions. One function to add add things to the mapping. So in this case, we're calling it add mobile number. And this time we're taking in two parameters, a string called name and an integer of a mobile number. And it's a public function, anyone can call it. And all we're doing is we're saying, in our mapping called phone numbers, we're saying phone numbers of this name, we want to store this number against that name. So that's kind of all that's doing there. And in terms of retrieving that data, we have a get mobile number function. This is, once again, it's a public function. It's a view function. It's not modifying the state of the chain. And it takes in a parameter, a string parameter called name. And all it's doing is it's looking up the phone number in the phone numbers mapping based on the passed in name. So once again, very simple example. We have a mapping. We add things to the mapping. We add names and mobile numbers. And then based on a name, we look at the mapping and then return the phone number for that name. So once again, I'm going to go to the compile tab, compile my contract, and I'm going to deploy it once again on the JavaScript VM. And once again, I have a deployed smart contract. This time we've got some new buttons here. So there's an add mobile number button here. And if you click on the drop down here, you can see there's two parameters that it takes. So we're going to add Alice, and her mobile number can just be whatever. And we're going to add Bob, and he can have a different mobile number. And we have a get mobile number button here. So you may have noticed that Remix puts orange buttons for any function that modifies the state of the chain or that needs gas, and it uses blue for any functions that don't modify the state of the chain, or just like a view or things that read the chain. So if I call get mobile number and I pass in Alice, I get Alice's number there, and Bob, I get Bob's number there. So that's it, guys, for the exercise. I'll put it over to you guys now. We'll let you play around for a few minutes. Reach out if you have any questions. If you're in the Zoom and you want one-on-one help, raise your hand and an instructor will hopefully get to you. And we will resume in how long? We'll give you guys a good 20 minutes, and that should hopefully give you a chance to have a bit of a break too, and get some water or a coffee or whatever you need to do.
If you guys raise your hand during the exercises, we're sending you direct messages on the chat, so keep an eye on that.
If you're asking for the full code, it should be in the exercise. You don't need to copy it from my screen. Yeah, and just to that point in the Zoom chat here, yeah, if you specify your variable in your smart contract as public, then there'll be an automatic getter function that kind of can be accessed or generated where you don't have to specify it. So that's why in this case there is a phone numbers function here, because we specified it as public. So if we specified public for number here, we wouldn't have to create this get number function. There'll automatically be one called number that we can use.
Hey, Mark, if you want to grab that link I just sent. Mark, paging Mark.
Just remember, guys, if you've got your hand up in the Zoom call, keep an eye out on chat for direct messages. There's like a little red thing that says direct message, where you'll get a URL from one of our helpers. You need to see that URL and click on it. If you don't see it and click on it within a certain amount of time, they may move on to someone else if there's other people that also need help. So make sure you keep an eye on the chat, guys, if you have your hand up. Thanks.
So just to answer a couple questions real quick that I'm seeing in the chat here. I see something like, hey, why are we using memory? What's going on here? The reason that we're using memory here is that strings are actually a special type in Solidity. They're actually basically kind of bytes squared. That's not a great way to put it, but they're like a special type of bytes, and they're an object. So we're basically just telling Solidity, hey, only worry about this for the duration of the function, versus like our uints and booleans and kind of those other variables aren't these special objects. So that it's really just for strings you need to do that memory thing. It's a little bit weird, but yeah, strings are basically special, and that's really it. Yeah, sorry guys, I'm helping people in another video.
Great question in the chat here. I noticed every time we redeploy the same contract to the Ethereum network, a new contract address is generated. In a real world scenario, how does the developer update an existing contract with a user already using it? So the answer is you can't update an existing contract once it's deployed. The blockchain is immutable, remember? So even if you deploy the same contract, it gets deployed to a new address and the old one still lives on basically.
There is a caveat there. There you can do you have to basically code specifically into your contract upgrades. So, and it's actually a really interesting topic. If you guys want to learn more about it, I've got a pretty sweet video on it. But yeah, you guys can do that a little bit later. The upgrade stuff.
Upgradable smart contracts are a bit controversial as well, because people argue that they're not as highly secure and tamper-proof if someone can change them.
I understand perfectly.
Looks like most of you guys have finished the exercise. That's really good news. Congratulations, you're doing awesome. We'll give the people who are still going a few more minutes before we continue. So have a break, grab some water, grab a coffee, whatever you want to do. And we will continue in 10 minutes from now.
Oh yeah, you got it.
Again, everyone, if you're in the Zoom meeting and you raise your hand, you have to be able to join a Google Meet. So if you're not able to join the Google Meet, maybe just try asking the question on the chat if it's possible.
Darkon, if you want to jump on, grab that link I just sent you, that'd be great. calling Patrick to the stage. Patrick, I just sent you a link if you want to click it. A lot of people are asking about the version of Solidity. Why are we using 0.6.7? Basically, we have a lot of really good examples with 0.6.7. Some of the examples are pretty simple. And it's really good to learn how to swap between versions because Solidity is changing a lot. So it's good practice to actually be able to swap back and forth between versions. Yes, there are jobs today that are just writing smart contracts. Some people are asking about some debugging tools as well. We will go into that a little bit more tomorrow.
All right, everyone, 2 minutes and we'll get going. Okay. Let's switch back. Awesome. So hopefully everyone was able to at least get the exercise complete and deploy it and kind of have a play with it. And just want to say congratulations, guys. You're doing awesome. Not only have you created and deployed a smart contract to a real Ethereum network, but you've also modified the smart contract and you've played around with arrays and mappings in Solidity, both very important concepts and used in many situations. So congratulations, guys. You're doing awesome. And you're taking some real big steps here. So you should be proud of yourselves. We're trying to cover a lot in a short amount of time. So I appreciate that for some people, we may be moving a little fast, but hopefully everyone's able to keep up at a decent pace. but we're going to continue now. And so we've talked about smart contracts a little bit. We've talked about Solidity. You've played around with smart contracts a little bit. You've created smart contracts that kind of modify the state of the contract. But these contracts are kind of these very simple things that just modify on-chain data in this case. But now we're going to learn about doing some cool things with the smart contracts. So with that being said, let's talk about the Oracle problem. So for those who may not know, we discussed earlier why smart contracts are so awesome compared to traditional digital agreements, but now we're going to discuss their basically biggest limitation, and that is that smart contracts cannot connect to external data or any off-chain resource on their own. And the reason why a smart contract cannot do this, as a traditional developer, you might say, well, you know, why shouldn't a smart contract be able to make an API call? After all, it's just code, right? And the reason for this is because the blockchain that the smart contract runs on is deterministic. And this means that all of the nodes are in perfect sync with each other when they're executing these smart contracts, right? They all execute them. They all need to reach the exact same output or conclusion for that smart contract execution. And if some of them reach one output or one kind of endpoint, and then other nodes reach another endpoint, then there's no way for them to kind of agree and kind of come to an agreement on what happened in that smart contract. So if reaching out to an API is part of a contract execution, there's a good chance that not all of the nodes will come to the same conclusion. Like the API might go down after some of the nodes call it, etc. So a smart contract needs to be told something. It needs to kind of, if you want to reach out to an API, it needs to be told what the result of that is, so that once that result gets passed back in and becomes an input into the smart contract, so that every single node on the blockchain takes that same input and then continues to process the smart contract. And that way everything's kept in this kind of walled garden, and everything's in perfect sync, and everything stays deterministic. So this is defined as the smart contract connectivity problem, not being able to connect to external data, systems, and events. And it actually limits smart contract functionality purely to things that can be done on-chain only, such as moving tokens around, paying people ETH or whatever the native cryptocurrency is, and things like that, which is cool, but once again, it limits the use case of smart contracts. So to interact with the outside world, we need what's called an oracle. An oracle is any device or system that interacts with the off-chain world to provide data or connectivity to smart contracts. So they report the result of the data or computation on-chain to the contract, so that the smart contract and the blockchain stays deterministic, like I explained earlier, and everything can continue processing in perfect sync. Having said this, using a centralized oracle actually creates a single point of failure in a smart contract and compromises the overall security of your system, basically, because you've got this highly secure blockchain, you've got a smart contract running on it. It can't be influenced, gamed, hacked, bribed, anything. But then you're triggering your smart contract from this one system or one oracle kind of running somewhere. And in the end, the end-to-end security of the overall system is no better than its weakest link. And in this case, its weakest link would be that single oracle. So to get around this, you need what's called a decentralized oracle network. And that's kind of what Chainlink is. Chainlink is a modular, decentralized oracle network for getting secure and reliable data on-chain and for triggering external computation. So we're bringing the data in or doing the computation in a decentralized way. And by doing this, we extend all of those really cool, unique properties that smart contracts and blockchains have that I explained earlier. We extend those out from the blockchain out into the data source and data delivery layer as well. So what this achieves is allowing contracts to take any input from the real world, add it on-chain as being able to take any output from the blockchain and then send it to the real world, but doing it in a decentralized way, right? So this end-to-end connectivity and reliability and security is the real value proposition of smart contracts, being able to perform the digital agreements that we have today, but to do them in a better, more secure, more reliable, more tamper-proof way. So to try to wrap your head around this visually, there's just like a simple diagram here where we have a number of Chainlink nodes fetching price data, and we can tell that they're fetching it from different sources because some of them have different numbers. And what they're doing is they're aggregating the result and they're kind of coming up with an average, and then that is then posted on chain. And one important thing to note here is that no single node here can directly influence the result that's posted because of this decentralization we have going here. It would take a number of malicious actors in this Oracle network to be able to manipulate this final value in any kind of meaningful way. So no single entity should have influence on the final result here. And by combining on-chain smart contract code with these off-chain resources and oracles that we're talking about, you actually have what we define as hybrid smart contracts, right? So these are smart contracts that rely on existing on-chain code and then combine it with these off-chain services and decentralized computation that oracles offer. So usually smart contracts are referred to as just the on-chain code part, but we're actually redefining what they are, and we're saying the combination of the on-chain code, the off-chain services, decentralized computation together is a hybrid smart contract. Now, you can kind of think of them as supercharged versions of a smart contract, and we're already seeing them going on to redefine what our industry is about these days in the form of DeFi and things like that. And it actually fits in really well with our belief that a smart contract is good at doing certain things, but not all things. And an Oracle network like Chainlink is actually responsible for everything that blockchains are not responsible for, or things that they can't do well. So Chainlink is also blockchain agnostic. We're alive on Ethereum, obviously, but also various other chains, Polygon, Binance Smart Chain, XDAI, many more to come. We're constantly rolling out on other chains as well. So we're not just an Ethereum-focused Oracle network. Cool. Any questions on Chainlink before we move on? Any questions in the chat to bring out? I got a fun little poll that I just launched for those in the Zoom chat. So what is the smallest unit of account of the link token? The correct answer there is joules, I believe. Cool. Okay, we might move on. There's a couple questions in the chat, but I think we've got helpers answering them there. So DeFi, probably most of you guys have heard of DeFi before. But for those who haven't, DeFi is taking all of the existing financial products available today, such as lending, borrowing, the ability to get yield and gain exposure and protection from events and risks and things like that, and taking all of those things and putting them on the blockchain and running them in a trust minimized way with smart contracts. Right, so basically we can perform these financial contracts with one another in a peer-to-peer way without these kind of rent-seeking middlemen such as banks and things like that. And in terms of the benefits this provides, without sidetracking too much, just quickly, it basically boils down to three things: greater transparency because of how blockchains and smart contracts are. Direct control over your assets because you control the private key that controls your asset, as opposed to, say, Robinhood controlling your private key and blocking you from accessing your assets. And also the ability to get superior yield to the traditional financial system, mainly because you don't have these kind of rent-seeking middlemen kind of in there kind of taking fees. So there's lots of examples of DeFi around today. But I'm sure lots of you guys have know plenty about this already. So DeFi is one of the most popular use cases for using a decentralized Oracle network such as Chainlink today, and a great example of what we defined earlier as hybrid smart contracts. So to go and kind of get DeFi rolling properly, DeFi needs price data from the outside world, from off of the blockchain. It needs to know the price of Bitcoin, the price of gold, the price of oil, whatever. So to get the DeFi industry going, Chainlink Labs created what are called price feeds or price reference contracts. And what they are basically these on-chain contracts. They're smart contracts, a collection of smart contracts. And what they are is they represent the price of an asset in the real world, such as the price of ETH, the price of Bitcoin, the price of gold. And you have a number of Chainlink nodes that all contribute to maintaining this price. And they fetch data from various data sources, and they basically all contribute to basically providing a market-wide price for that asset that developers can then use in their smart contracts whenever they want to create DeFi applications or any smart contract that needs price data. So just this diagram here is a good example where we have a number of Chainlink nodes here grabbing price data from exchanges as well as data providers and aggregators. And then they're kind of doing some aggregation on the price data, and then they're posting a final result on chain, which other smart contracts can then reference. For those who just asked, how often does Chainlink update? Whoops, sorry, let me just, I lost myself there. For those who asked, how often does Chainlink update? I might just go to the site and show you guys. So that's not the one. So if you go to data.chain.link, you can see the available feeds on mainnet. So I'll just go to the Ethereum USD feed. Hopefully that's big enough. So as you can see here, we have 31 Oracle nodes on the ETH USD price feed on Ethereum mainnet. So they're all contributing to maintaining the price of ETH on this price feed. And the way it works is there is a deviation threshold. And what that means is if the price of ETH is more than 0.5 off of what this current answer is here, then the operators will post an update to the price. Or if it's not more than that deviation threshold, there is a heartbeat that kind of expires, and I think it's currently set to 1 hour. So if there hasn't been more than a 0.5% move, then every hour they'll update the price anyway. So depending on how much the price fluctuates, the frequency can kind of be anywhere from within, a short amount of time up until an hour. So yeah, I explained how each node independently gets data from various APIs, exchanges, high quality data aggregators and things like that, and they report the answer on chain. So the reason for having this kind of such highly secure and tamper-proof data delivery mechanism, and we saw for the price of ETH, there was 31 nodes delivering data there, is because of DeFi attacks and DeFi exploits. So we see DeFi attacks all of the time. You guys, I'm sure, see them in the crypto news and stuff as well. A lot of them are due to things such as using centralized oracles or not having sufficient market coverage in your kind of oracle mechanism design. So if you just get data from a single exchange, that can kind of be manipulated. Whereas in the case of Chainlink price feeds, we actually have a high level of market coverage. So you can be confident that that price you see on the price feed represents the whole market, not just one exchange or two exchanges or three exchanges. Cool, so we're actually up to the next exercise now. So these exercises, we're going to still do smart contracts and Solidity, but we're gonna do some Chainlink stuff with them so that you can still get a feel for what it's like to create, deploy, and interact with smart contracts, but you also get a feel for what it's like to use some of the Chainlink tools and features as well. So once again, I'll just do a quick demo first, and then I'll let you guys play around with it next. So the code is in your exercise. I've probably got one completed here already. Hopefully you guys can see that. So I'll just run through this for a few minutes and then you guys can have a play. So in this example, once again, we're specifying our Solidity version here. And we've created a new contract here. We're calling it a price consumer contract. And in this case, we're actually importing one of the Chainlink smart contracts here. So aggregator v3 interface, we're saying we need to use this smart contract code in our contract here. We're creating an instance of this aggregator v3 interface contract here. We're calling it price feed. This is an internal variable, so only accessible from inside the contract here. We have a constructor function here. So for those who don't know, a constructor is kind of like a function that gets executed just once when you first deploy a smart contract. So it gets deployed on contract creation. It gets executed, sorry, on contract creation, and then it's kind of just, that's it. It never gets executed again. So in this case, we're setting the value of this price feed variable to, and we're calling the aggregator v3 interface contract here, and we're actually specifying an Ethereum address here. So what this Ethereum address is we're specifying what the price feed reference contract is we want to use. So if I go back to the price feed kind of user interface here, each of these price pairs has a deployed smart contract that you need to reference if you want to use that price data in your contract. So if you go to the Chainlink docs at docs.chain.link and you go to using price feeds, Ethereum price feeds in this case, if you go down to the Kovan testnet section here, you can see all of the price pairs available here for you to use, and each one has an address. So if you want to use the ETH USD price pair or price feed in your DeFi application or in your smart contract, you basically go here, you literally copy the address, and then you kind of paste it in here, and that's kind of what we've done. So we're saying we want to use the Ethereum USD price feed in our smart contract here. And all that we've got here now is we've got one function here called getLatestPrice. It's a public function. It's a view function. It doesn't modify the state of the chain, and it returns an integer in this case. And all we're doing is we're calling the latest round data function from this price feed thing that we've created up here. And it's basically returning a bunch of information to us. The current round of the price feed, a round kind of gets set every time the price is updated, a kind of new round gets set. The current price, when the round was started at, and the timestamp and when it was answered, and when it was answered in the round, sorry. So in this case, all we're interested in is just this price here. So all this is doing is it's kind of saying, okay, all of this information in the current price feed, I want to return the current price. And that kind of gets returned as an integer. And that's it. It's that easy. If you want to have a high quality decentralized price data in your smart contracts, it's literally a few lines of code to use these Chainlink price feeds. And these price feeds, you can ignore the warnings here when you compile. These price feeds are actually securing billions of dollars on mainnet across various DeFi protocols already. So one thing to note when you deploy your smart contracts, because we're using the Chainlink Oracle network now, you need to do it on the COVID network. You can't do anything locally in Remix here because Chainlink the Chainlink Oracle network does not know about your local Remix kind of virtual machine Ethereum thing. So we're doing everything on Kovan now. And when you deploy your compiled contract, in this contract drop down here, make sure you select the price consumer contract and not the aggregator one that you imported. So you just double check that you've got the right contract here. So we're going to deploy that contract and we're going to confirm the transaction in MetaMask. So hopefully you guys are getting used to this whole deploy confirming transaction type thing that you need to do. And then we get our deployed smart contract down here, and I call the get latest price. And as you can see, we get the price of ETH USD. It's padded out with to a bunch of with a extra position, basically because we don't have floating point numbers in Solidity. We want to ensure we've got enough numbers padded out so that if you need to do arithmetic or anything, we're not going to kind of run into issues. So, and you can then go back and compare this to the mainnet one, and it's probably not going to be exactly the same, but it's probably should be similar. So there you go. So that's literally it for the next exercise, guys. You're creating another smart contract. You're deploying it to Kovan. In this case, the smart contract is using a Chainlink price feed, and we're kind of interacting with that and getting some, we're getting price data in our smart contract. So we'll leave it for you guys to play around with. We'll give you a bit of time, and if you have any questions or issues, reach out to us and we'll try to help you out. And if you have any questions on price feeds, now's the time to ask, or just ask in the chat as well.
So I see a lot of questions on why Link is being used and not ETH. There's a lot of reasons why a blockchain protocol needs its own token. But some of the main reasons are Link needs to be blockchain agnostic, so it needs to work on multiple blockchains. It can't rely on one specific blockchain's native currency. It needs its own token for staking eventually, and properly incentivizing the node operators. If you rely on a different token like ETH, it ties in incentives with the ETH blockchain. So hopefully that makes it a little bit clearer why all these requests are paid for in Link.
There's a really good post that Vitalik posted that I just posted in the chat, and I'll post it in the YouTube as well, where he is basically saying that the Ethereum-based system does not know about what the price of an asset is, in the outside world or anything like that. And the Ethereum should always be this completely decentralized and apolitical and completely impartial system that has no affiliation or bias towards anything. And by using Ethereum, by tying the Ethereum token to whether a fact about the outside world is true or not, you're actually imposing political risk on the platform.
So yeah, another question people are asking is, hey, well, how come when I call get latest price, it's not, I don't have to pay any gas, it's just coming up. But when I deploy this contract, I only have to pay ETH. What's going on with this gas stuff? So what's going on is that this contract on chain, this price feed contract, at that address where you see it says aggregator v3 interface, and then there's that address right there. That address has already been delivered data. It's already been delivered pricing data, aggregated pricing data on chain. This means somebody else has already requested that data. Somebody else has already paid the oracles, the Link token, to get that data on chain. So the reason that you don't have to work with the Link token for this particular contract is that somebody else already has. And we're just reading the state from that contract that already has that aggregated data, that aggregated answer. And as we know, since it's a view function, when we just read state off the blockchain, that doesn't cost any gas. So that's very nice. And no, this does not mean you could be reading really old data, right? Because you can even check some of those other answers. If you see that price feed.latest round data, right, in that get latest price function, it gives you, hey, this is when this was updated. This is the timestamp here. So if you wanted to, if you were nervous, you could always check the timestamp. You could check started at. You could check a lot of these different other returns that get returned with that latest round data to just make sure that you're getting the most up to date. But yes, the latest price is constantly updated. So,
yep, great answer. And there's a good question: how much does it cost Chainlink to put price feed data on chain? So previously, the way price feeds worked is that every single node in the price feed whoops, wrong screen. Every single node in the price feed here, we're posting their response on chain, and then the aggregation or averaging was done on chain. Now that OCR has gone live, it's changed, and the costs in terms of the transaction fees has gone down by a huge amount. And just at a high level, what OCR does is the Chainlink nodes all talk to each other, and they all say, hey, I got this answer, hey, I got this answer. And those answers are all signed, and then a single report is generated that contains the responses, and then that report is then sent on chain. And it's not just a pure averaging. They are volume. They take volume into consideration as well. So one single exchange with very little volume is not gonna. Their answer is not going to have the same weight as a major exchange that has the top or second or third top volume for that kind of asset, basically. And yes, timestamps are always epoch UTC format. There's no date formatting generally in Solidity, or none that I'm aware of.
for those of you getting that abstract error that you're running into, if you go look at contract in your compile or your deploy part, you just want to switch to price consumer v3, exactly as Harry has shown here. So you're probably getting that abstract thing if you're on aggregator v interface. So you want to be on that price feed, consumer v3.
Sometimes Remix tries to throw you off, and by default it would choose the thing that you're importing other than the one that you're actually creating. So you just have to be aware of that.
A lot of people are asking about the get latest price and the get latest round data return. So what's happening there, if you want to scroll down real quick. This one right here. So latest round data actually returns multiple different types. It returns several variables here. So it's not an array. It's what's called a tuple. And it's just several types. So if you see like above, like our function here, get latest price, it says public view returns an int. We could do like a comma, and we could do a whole bunch of stuff in there, and that would be the same thing. So so that latest round data function just returns a lot of different variables.
For those who are asking about the code of the aggregator v3 interface, so all of the Chainlink smart contracts and code in general is open source, and it's on our GitHub. So you can go to the GitHub repository here, I'll post it in the chat, and you can search for your smart contract that you want to see the code for. Or if you just go to contracts, source, and then depending on which version, and you can see all of the code in the GitHub repository. to find the price feed addresses. Like I said, if you just go to docs.chain.link, and if you go down to the using price feeds section here on the left, there is a contract addresses link here. And then if you go to the Ethereum price feeds URL here, you can see all the Ethereum mainnet addresses. And then if you just scroll down past those, you should find the Coven testnet price feed addresses here.
And Frederick, I sent you a message with a link. If you could click on that link and I can help you out.
Looks like most of you guys have finished the exercise, so take a bit of a break. We'll probably resume in about 10 minutes. So we'll give those who are still going a chance to complete it.
Calling Mr. Tharun. I just sent you a link to Google Meets.
Just to reiterate, guys, when you're deploying your contract, very important, this contract field here, just above the orange deploy button, make sure it's set to the price consumer v3 contract and not the aggregator v3 interface one. It'll help you get over errors and issues that you may have. So make sure it's set to the price consumer v3 one before you hit that deploy button.
Calling Chi to the, I sent you a link, Chi. Hey all. So Chi just asked a great question, and I've seen a number of people ask this as well. They're talking about how do you deal with these huge numbers, right? We see here gate lattice price. It looks like it's this massive number, right? How do you deal with these floating point numbers? What's going on here? So in Solidity, as you guys know, decimals don't actually work. We need to work with these whole numbers, right? And there's a lot of reasons for that. One of the reasons is we really don't want to round stuff off, because we might lose people a lot of money. So by convention, all of these values have some understood number of decimals, right? And these price feeds, they actually have a function called decimals that we can call to see exactly how many decimals each one of these prices have. It's not shown here, but if we did like price feed dot decimals, and if you wanted, you could even try this out yourself, trying to write like a little decimals function. Yeah, exactly like that. It would return, I think, a uint8, which says how many decimals it has. Now, once you know how many decimals something has, you can go ahead and modify, and do all your math so that everything matches like the correct number of decimals. And actually, yeah, Harry, it looks like Harry's trying to build it right now. You can get all your units to have the same amount of decimals, and then you can kind of do math normally. There is a caveat here. Obviously, if you're trying to divide something and you're, maybe 1 divided by 2, right? You can't actually get 0.05. So what you would need to do is you would need to multiply it by 10 first, or some number, right? And then divide. So that you can end up with a whole number. And this is why we have terms like Gwei and Wei that you might have seen, where Wei is the smallest unit of Ethereum. And then, Harry asked that wonderful question, like, what's the smallest unit of Link, which was a joule? 1 ether is this massive number of Wei, and it has 18 zeros, right? So that's how you can basically work with these floating points and work with decimals, is you just represent decimals as really, really, really big numbers. So hopefully that makes sense, and hopefully that clears some questions up here.
We'll move on, guys, in 3 more minutes. For those who want a good site to kind of work with decimals in Solidity or Ethereum in general, this one's really good, ethconverter.com. So you can literally put in 1 ETH or 1 link in this case, and you can kind of get, excuse me, the value in Wei here, or 0.1. Whoops. There we go. Okay, guys, let's move on. So make sure I'm still sharing. Yes, all good. So hopefully everyone was able to play around with a smart contract that makes use of Chainlink price feeds there. So once again, we're getting that muscle memory of creating smart contracts, deploying them to COVID, paying the gas, interacting with our MetaMask wallet to deploy them. And in this case, we're interacting with a smart contract, and the smart contract is reaching out to a Chainlink price feed on the Ethereum COVID network, and we're getting that price data in our smart contract so that we can then use it for whatever we kind of want to use it for, whether it's to do things in a DeFi application or whatever. So hopefully you guys had a bit of fun with that one. So now let's talk about accessing any API using Chainlink, because Chainlink is more than just price feeds. Chainlink provides the ability to connect to any API that you want. And this can be an API on the web, a simple HTTP GET or POST request. It can be connecting to an enterprise database or system, an IoT sensor, any API-enabled device. It can be a fridge, a washing machine, a car. If it's got an API on it that can be accessed, then you can connect a smart contract to it using a Chainlink Oracle. And the way this works in terms of the kind of flow of events is it's what's called a request and response model. So you have a smart contract that makes a request. It says, all right, I want this Chainlink node here, or these Chainlink nodes if you're doing multiple. I want to reach out to this API here, please. And it provides whatever details it needs to provide. And then that's a transaction that kind of gets recorded. And there's actually what's called an Oracle contract that sits between a Chainlink node and then other smart contracts, and that kind of acts as like a middleman to kind of pass requests and things. So the consuming smart contract says, hey, I want to reach out to an API, this API. Here are the details. Here is some link for that request, because we need to pay in the form of link to do that kind of off-chain data request or computation. And then the Chainlink node will receive that request. It will reach out to the API, and then it will, depending on the case of what the job is, it will kind of maybe parse the response and do some kind of formatting or something, and it will send the response back on chain. And that's a completely separate transaction. So that's the response transaction. And then the original smart contract that did the request for the API will get that response stored or kind of passed into a function. So it's a request in one transaction, and then we wait for the Chainlink node to process the request, and then the Chainlink node posts the response back. So it's not a synchronous thing, it's asynchronous. So it's not like when we were reading from the price feed contract. This is like a multi-step scenario here. So Chainlink nodes have what are called adapters that are used to reach out to APIs. And if it's just a normal HTTP GET or POST request, then you can use kind of the core adapters, and then you can kind of do things in them such as parse out the response and kind of take parts of the response, which you'll see in a minute. But we have what are called external adapters too. So these are kind of custom. They're pretty much an API in itself. They're like a custom API that has a specific input format and output that's defined that a Chainlink node can then use to connect to any API. So if you need to read a file from some database, or if you need to connect to IPFS, or if you need to do whatever you want and it's not available with a Chainlink core adapter, you can build your own custom external adapter. That custom external adapter can then get used by a Chainlink node in a job to then do that request for you. But that's kind of a bit out of the scope for kind of this first session. But I'll just say that there's a website called Chainlink Market, which is really good for finding jobs. So whether you just need to do a simple HTTP GET of a number, or whether you want to get the price of ETH USD, there's all kinds of jobs here. So there was a real estate one here too somewhere. Don't know what that is. But so in this case, you're going to do a demo in a minute, which just does a simple HTTP GET. And in this case, we're just getting a number. So here's an example of a job that does that here. I won't go into it too much, but essentially, in this case, it's doing a HTTP GET on a specific URL, and then it's passing the response, and it's padding it out with a few zeros, and then it's kind of posting the result back on chain. But for now, I'm just going to show you and walk through the code actually of the next exercise, and then you guys can have a bit of a play around with it as well. So much like the last example that we walked through, where we're importing a library, in this case, we're importing the Chainlink client library. So if you want to reach out to an API using Chainlink, you need to import this library, and then we're saying our API consumer contract is using this library here. So what we're doing in this smart contract is we're reaching out to a simple API that returns some crypto information. And in this case, we're actually grabbing the volume of Bitcoin or Ethereum or something. I can't remember which one. So we're creating a volume parameter here. And then we're creating 3 other variables here. Sorry, not parameters. One is an Oracle. It's called Oracle, but it's an address type. And then we have what's called a job ID, which is a byte array here, a byte string, and then we have a fee in link. So every time you want to do a request for to reach out to an API, you need to specify a job ID, and the job ID is basically defined on the Chainlink node that you want to use. So going back to market.link, here is the job ID for this job here. So and the fee, so every job might have a different fee. If I take a look at this one, the fee is 0.1 link for this Coven job. And the Oracle address here is the address of that Oracle contract that sits between the node and other smart contracts processing requests. In this case, I think it's looking at this address here. So they're the 3 things that we kind of need. And once again, we have a constructor here, and this constructor has this function that's from the Chainlink client here, which basically it sets the address of the link token based on what network you're on. So in this case, it will go, okay, this person's got a contract on the Coven network. The address of the link token on the Coven network is, this address here. I know what it is. And in our constructor, we're just setting the Oracle and job ID and fee to a specific job. It's probably not this one, is it? No, it's another job, but it's probably very similar to this one. It basically just does a HTTP GET, and then it passes the response, so you can kind of strip out and get a single value in the response, and then it multiplies the result by something which you'll see in a minute, and then it posts the response back on chain. So we're basically just specifying which job we want to use here. And then we have 2 functions here. We've got our request function, and then the fulfill one, or kind of that response transaction that I was talking about. So the request function, it's a public function, and it returns a request ID. And all it's doing is it's creating a new request here, chainlink.request from the Chainlink library, and it's calling this build Chainlink request function, and it's passing in the job ID that we defined in the constructor that says, hey, this is the job ID I want to use for this job. It's specifying the address of this smart contract here that we're currently looking at to say, hey, when a response comes back, it needs to go back to this contract here. And we're actually specifying the fulfill function here. We say this dot function name dot selector, and that basically says when you get a response, this is the function that you need to call. Basically, when the Oracle gets a response and sends it to the Oracle contract, the Oracle contract should call this function. So once that's done, we're basically just adding things to the request before we send it out. So we're saying we want to do a HTTP GET on this URL here. And I'll just go to the URL so you guys can see what the API call is. So you can see the API call is just a whole bunch of data for the ETH USD price pair on the crypto compare API. And I think in this case, we're looking for the volume 24-hour value here. So we're saying request.add path raw.eth.usd.volume 24 hour. What this does is it says when you get a response from the API, when you get all of this stuff back, I want you to traverse down and go to raw ETH USD volume 24 hour and then grab this number here. So that's kind of what we're saying there. So I'm going to say hit this API, grab whatever it returns, and then traverse down this path and grab us this value here in the response. Then we're saying we want to multiply the result by 10 to the 18 to kind of pad it out for those reasons that Patrick was discussing earlier. And then once that's done, we're all ready. Send the Chainlink request, send the request to reach out to the API. It will go to the Oracle contract. The fee is going to be paid at this point, and the request will get sent. And the Oracle contract will grab the request. It'll kind of emit some data to the blockchain, and the Chainlink node that runs this job that we specified is going to look at that and see, oh, there's a job for me to process, and it will do the job, and then it will call this fulfill function, which just sends back the volume parameter here. It sends back the volume that it gets from the API. And all we're doing in this smart contract is we're just storing that volume data in the smart contract here. So just a very simple kind of request and response. So I'll just quickly demonstrate it for you guys. Once again, make sure you deploy the correct contract here. So in this case, it's the API consumer contract. Now this is a little bit different from the last ones that we did, because once you deploy, you can't just call request volume data. You're going to get an error, and that's because we need to, when you call that, we're actually doing that request and call thing where we're sending a link payment for the off-chain computation that we're doing, and we're also doing the request for the API at the same time. And the smart contract has no link in it right now. So it's trying to send a link to the Oracle contract, which will send it to the node, but there's no link in the contract. So to get around this in Remix, we need to copy the address of the API consumer contract here, and you need to go to your MetaMask wallet and go to your assets. You should have the link token listed here. If you don't, check the setup instructions. It will tell you how to do that. You click on that, and then you go send, and we paste in our smart contract address that we copied using this copy button here, and we'll send it some link. I think we only need to send it 0.1 actually, but I sent it 1 anyway. And we wait for that to confirm. Cool, that should be done now. And once that's done, we should be able to successfully call request volume data. Cool, so that's successful. I can take my contract address and have a look at it in Etherscan as well, right? And you can actually see there's an ERC20 token transactions tab here. And hopefully in a minute, we should see this update. There we go. So there was a transaction where I sent 1 link token to the smart contract, but now in this latest function call that I did to request the volume data, we can see that 0.1 link actually went out to the Oracle contract here. So if I press the volume button, hopefully it's been long enough. So there we go, we have a response. So the Chainlink node received our request, it reached out to the API, it grabbed all of this JSON data, it traversed it and then stripped out this volume 24-hour number. I'll just refresh that. It multiplied the result by 10 to the 18, and it then sent the response back, and that response made its way back on chain into our fulfill function here that we specified up here. and we then store that value in our smart contract here. So there you go, just another cool example of deploying a smart contract, doing a bit of stuff in Solidity, but more importantly, reaching out to an API in your smart contract, or reaching out to a Chainlink Oracle, which reaches out to an API, so that you can then get off-chain data into your smart contract. So I think that's it for the next exercise. I'll now hand it off to you guys to have a bit of a play. If you have any questions, you can ask them now or ask them in the chat, or if you need help, put your hand up in Zoom or ask in the chat in YouTube. We'll give you guys a good maybe half an hour for this one. So we will resume at about 2 ET. So just to reiterate, once you deploy your contract and you have it down here in your deployed contracts section, you can't do that request for volume until you fund it with Link. And to fund it with Link, there's this copy button here next to the contract address. You literally press it and it will copy your contract address onto the clipboard. And then in your MetaMask wallet, you change your asset to the Link token and you can paste your address in, and you can send it enough Link for the API request. And once that transaction is confirmed, then you can press your request volume data button to execute that function. And yes, this is just a simple example to demonstrate reaching out to an API. However, as I explained earlier, this is, in this case, we're grabbing price data from a single data source using a single Chainlink Oracle, which is not advised if you're building an application where you want any kind of decentralization and high level of security and tamper resistance. So the 0.1 link goes to the Oracle contract first, that sits between the Chainlink node and other smart contracts, and that Oracle contract passes it on to the Chainlink node. So every Chainlink node has their own Ethereum wallet address as well, and they kind of collect that payment. So the Link token could be thought of as like a gas kind of for oracles doing off-chain requests and computation. Just a reminder, if you're trying to fund your contract with Link, once your contract is deployed, down here in the deployed contracts section, there is a small copy icon here to the right of the name and address. If you press that button, it will copy your deployed contract address to the clipboard.
Just a little bit more context, because I've seen a couple of people talk about this stuff. This request and receive model that we're doing here, this is basically what the price feeds are doing on the back end, right? You know how before with the price feeds, we didn't have to go through this process of sending link. We could just read directly off the contract. Well, that's the equivalent of just hitting that volume button that we have here, right? With the price feeds, we could just hit get latest price, and it said, here you go. And we were just reading right off the chain. We're doing that exact same piece here with the volume piece, but we're doing the step before, which is requesting the data using the link token and getting it returned. So on the back end, there's a whole bunch of sponsors who are actually running through this process automatically to keep updating those price feeds doing this. So a way to think about this is a whole bunch of these API calls put together builds and creates these price feeds. So this is kind of like the smallest unit of what's going on behind the scenes of these price feeds. So hopefully that clarifies some things here.
If you finish the main exercise, feel free to have a couple-minute break or play around with the bonus stuff. We will probably resume in the next, in about 3 minutes from now, just to make sure we don't run over time.
Yeah, and then here's another question that gets asked a lot, and a couple people asked here. It's a really good question. So people are saying, hey, well, if I'm just making an API call here, why don't I just like scrape the web and then put the data into the smart contract myself? Like, why should I even bother going through this process? And that's a great question. And the answer is, well, are you going to do that forever? What happens if you get bribed? What happens if you are a malicious actor? As Harry was saying before, we want to move away from this world where we have to trust these brands, right? And if you're the one providing this data to your decentralized smart contract, well, guess what? Your decentralized smart contract just shot itself in the foot and is no longer decentralized, right? Because now you are the one who controls all the data. You are the single point of failure now. So your smart contract is no longer decentralized and kind of defeats the purpose of building on the blockchain in the first place. Like go build your application, in Python or Node.js if you're going to do that. So it's a really, really good question. And that's why I was talking a little bit before about how this is kind of what's going on behind the scenes for the request and receive, right? Doing this one API call alone to a single node with a single API is probably not a very secure way to build a smart contract, right? Because we have these single point of failures. And this is why the price feeds, they do this in the back end with many different APIs and many Chainlink nodes. So absolutely fantastic question. Hey, why don't I just do this myself? Well, the answer is basically, okay, well, do you want it to be decentralized or not? And if yes, then you can't do it yourself because then you are the single point of failure. You've become what you swore to fight. Yes, I love that. That is excellent. Excellent.
Awesome. All right, everyone. I think most of you have finished. There might be still a few people going. We have got one more exercise, so we are going to move on now. And then we'll kind of close things off. So let me just switch back to the slides. Cool. So hopefully you guys were able to successfully create, deploy, and interact with a smart contract that reaches out to an API. And if you have completed that, then once again, congratulate yourself and pat yourself on the back because you just did your first request for external data in a real smart contract deployed on Kovan, and it actually reached out and a real Chainlink node received your request and sent a response back on chain. So awesome work, guys. And now we're going to talk about Chainlink VRF. So Chainlink's more than just price feeds and then reaching out to APIs. It also provides the ability to do off-chain computation, like I said before. And one of the more pressing needs for off-chain computation that's come around in blockchains is the need to implement a truly verifiable random number generator. Now, random numbers have been used for thousands of years, actually. So whether it's rolling the dice or flipping a coin, what's trying to be achieved is always basically just coming up with something random or kind of leaving the result to chance. And random numbers in a computer, or pseudo-random numbers in this case, are similar. They're an attempt to achieve an unpredictable random result. But until recently, getting random numbers on chain has kind of been a bit of an issue because the previous methods were to use use on-chain data to come up with a randomness, which is risky because blockchains, once again, are deterministic, and certain on-chain data can be premeditated or influenced by miners, or to use a centralized API, which, as we discussed earlier, is prone to being hacked and influenced and things like that. And we actually see exploits happening in contracts that use randomness as well. So not just DeFi exploits. People exploit smart contracts that don't implement proper sources of randomness in their smart contracts. So what Chainlink VRF does is it brings a solution to generate provably random numbers. Now, if you're asking, well, what the hell does that mean? Basically, it means that if you have a smart contract and you say, hey, I want a random number, a Chainlink node will basically get you a random number. And when it sends it back, that random number actually gets verified. And how it gets verified is that the result is verified that it actually came from that Chainlink node and not someone pretending to be that Chainlink node. So we use kind of public key encryption to sign messages and things like that, and we verify that. And B, it actually verifies that the random number came from the given seed that was passed into the request for randomness. So when you do a request for randomness with a pseudo random number generator, you need to have a seed, which is basically just a source of input for the random number generation, right? And in the case of Chainlink VRF, I think it's comprised of a few things such as the public key of the oracle, as well as the hash of the block containing the request. And there might be one or two other things there too. So the flow of events is a smart contract says, hey, I want a random number. There's a contract called the VRF coordinator contract that kind of sits in between any request for randomness between a Chainlink node and smart contracts. And that kind of takes a request. It kind of builds up a seed with kind of the things I spoke about just before, and then it sends it to the Chainlink node. The Chainlink node gets a random number using the seed, and it signs the response, and it sends it back to the VRF coordinator contract on chain, and the VRF coordinator verifies that the response came from the Chainlink node and that the random number was created based on the seed that was given to the Chainlink node, and that it's not some random number that was specifically put in by a miner to kind of influence the smart contract or anything like that. And then if that verification passes, if that kind of special verification passes, then the random number is sent back to the smart contract on chain, and it kind of sits there, and then you can do whatever you want with it. So similar to the API call, it's this kind of request and response pattern, where we're paying Link for the off-chain computation, or in this case, the random number generation, and then we're getting a transaction coming back with our random number. So there's a number of interesting use cases using this in production already. One of the more popular ones recently is minting NFTs with provably random traits. So you can use Chainlink VRF to mint NFTs with various traits in a provably random fashion. Gaming is also a really big use case too. It's absolutely blowing up lately, and I think it's going to continue to be very popular. When it comes to games, people that participate and play them, they want proper randomness. They don't want kind of premeditated things happening all the time. So that's it in terms of the slides. I'm going to just run through a quick demo of the VRF code that you guys are going to run through. So once again, we're just going to play around with a smart contract, get you some more experience in deploying and interacting with contracts in Remix and kind of funding contracts and things. But in this case, we're going to do a smart contract that does a request for randomness. So very similar to the API contract that you guys just did. In this case, we're using the Chainlink VRF consumer base contract though. And in terms of the variables, where we're kind of setting, where we're storing the random number in this kind of random result number here. And in terms of what we need to pass pass to the VRF coordinator contract when we want to do a request for randomness, we're passing the fee and the key hash and probably a couple other things, so which we'll go through now. So in the constructor for the smart contract, we're calling the VRF consumer base constructor here, and we're passing in the VRF coordinator contract address, which I'll go through in a second, and the link token contract for the network that we're on. So in this case, we're on Kovan. This is the address of the link token on Kovan. So you might think, well, what do I put in this VRF coordinator contract address field? So because we're working on Kovan, what we do is we go to the Chainlink docs again. And in this case, we go down to the using randomness section here, and we go to contract addresses. And if you go down to Kovan, somewhere here, you can see it says, here is the value of the link token on Kovan. Here is the address of that VRF coordinator contract on the Kovan network that sits in between the Chainlink node or nodes and smart contracts that request randomness. And if I go back to Remix, we're also setting a value in this key hash variable here. So this is the public key, the publicly broadcasted key of the Chainlink node fulfilling VRF requests on Kovan. So you're saying, hey, this is my address. If you want to send me requests, send them to the coordinator, but this is my address basically. And then the fee is 0.1 link. So that's it for the constructor. And the rest of it's very similar to the API call. We have two functions, our request and then our kind of response one that gets called when we get a result back. So our request function is called get random number. It's a public function. It returns a request ID there. And there's a bit of a check here that checks if the contract is funded with link, and if not, it will throw an error. I don't think we had this in the API call one actually, but essentially all this is doing is it's calling the request randomness function from the VRF consumer base contract, and it's passing in the public key of the Chainlink node that's going to be doing our request for randomness and the fee amount. So this will basically send the request to the VRF coordinator contract, and the VRF coordinator contract will send it to the Chainlink node. The Chainlink node will do the request for randomness, and it will send the response back to the VRF coordinator contract, and that will then verify that it's a proper random number created with the seed and that it was from the Chainlink node, and then that will then send the response back to this fulfill randomness function, and we'll kind of get it back in here and we'll store it in a variable. So you'll notice we haven't specified this function anywhere in this get random number function like how we did in the API contract, and I think that's because you need to have this, the VRF coordinator will specifically look for a function with this name and this signature on here, so you kind of need to call it this, I think. Correct me if I'm wrong, Patrick or Zach. So we'll get the random result back here, and then that's it. We have a verifiably random number in our smart contract. So very similar to the API exercise, I'm going to compile, deploy my contract. And once again, make sure you've got the correct contract specified in the contract LOV here. Once that's deployed, I'm going to copy the contract address and I'm going to fund it with some link. Now that that's complete, I'm going to call my get random number function here. That's confirmed. So once that's done, we'll wait a few seconds. If I call this now, we're not going to have a response yet. So that will go to the Chainlink node. The Chainlink node will fulfill the request for randomness, and hopefully in a few seconds, we should get a response back. And there we go. So there's our random number. It's a really long number. You can do whatever you want with it after. You can do math operations or modulus operations to kind of make it like a number between 0 and 100 or 0 and 1,000 or whatever you want. But we'll let you guys play around with that in the exercises. So that's it for the demo. We're basically just creating a new smart contract. It's a contract that will reach out and request randomness from a Chainlink node, and then it will kind of get that random number back from the Chainlink node. So we'll leave it to you guys to have a bit of a play. If you have any questions on VRF in general, feel free to ask them now. Otherwise, yeah, reach out to us if you need any help using the normal kind of processes that we've been going through the past few exercises. We'll give you guys a good, how are we doing for time? We'll give you guys a good 15 minutes on this one. Hopefully that's enough, and then we'll wrap things up.
Got a couple people talking about the fulfill randomness function and what role that it plays. So I wanted to just go into it a little bit deeper. And then Harry, I missed your question. I think you said, hey, like, correct me if I'm wrong, but I missed it. I was helping somebody. Actually, yeah, maybe we'll start there. What was that? What was the, what did you ask, Harry?
I think, was it that this function needs to be called fulfill randomness, right?
Yeah. Oh, okay. So it was around the fulfill randomness. Okay, cool. So yeah, so I'll go into that a little bit more. So what's actually happening is this is still following that request and receive cycle that we just saw with the API calls, right? We made a request. to a Chainlink node in transaction. And then in a second transaction, the Chainlink node responds. And in the API call, it responded to that fulfill function that we defined. Now, in the randomness, these randomness contract automatically looks for this function called fulfill randomness. Okay. And you even see in your little contract on the left, you see this raw fulfill randomness, right? And so people are like, wait, what's this raw fulfill randomness? What's going on here? So we are inheriting a lot of functions in this contract, right? If we look at the top of the contract, we say, random number consumer is VRF consumer base. We're inheriting all these different functions from VRF consumer base. And one of those functions is raw fulfill randomness. So that's a function that we're inheriting from the VRF consumer base. We can ignore that. The reason we can ignore that is because that is what the VRF coordinator is going to use. Hopefully you guys are still with me. So we make a request for a random number. Chainlink node goes, okay, great. I'm going to return. But instead of returning it to this contract that we've deployed, it actually sends the random number to the VRF coordinator address. It sends it to that address, and then that smart contract is the verifier to make sure that the number that we've sent is actually truly random. And then the VRF coordinator contract technically calls this fulfill randomness. So it goes through that process. We make a request, Chainlink node makes the random number, responds to the VRF coordinator then calls the contract that we deployed. If that's a little bit confusing, the way I usually just say is, hey, just think of it exactly the same as request and receive. We make a request, Chainlink node responds to this fulfill randomness function, and that's really it, right? And we can ignore that raw fulfill randomness because that is being used by the VRF coordinator. We don't need to worry about that. So hopefully that makes sense. And a couple people are asking about like, oh, well, what's override? What's going on there? Override is a keyword basically says, okay, this method is going to override some other method internally. So this fulfill randomness is also being inherited, and we're just going to override the initial implementation of it. So we're saying this is the real fulfill randomness. Don't use the other one that is defined internally. So hopefully that makes sense.
Yeah, so I see some people asking about lag in the get random number. Kind of like what Patrick was saying earlier, this kind of like async operation, right? Request, receive. And every time we ask get random number, we call that method, we have to write a transaction to the blockchain. And then the VRF node, once it gets that we've sent that transaction out, it has to write a transaction. So we have to wait for these transactions to be added to the blockchain before the number is shown.
Praveen, if you want to grab that Google Meets link I just sent you.
You better wait here. I'll be back in 10 minutes.
Even 10 minutes is a long time to be away from you.
Looks like most people have completed the exercise or are doing the bonus one. We'll wrap things up in another 3 minutes. And if anyone still has any questions or issues, they can reach out to us in the Discord after that. In addition to that, we're going to send out a link with a feedback form. It'd be great if you guys can fill that out and give us some feedback on today's session as well. Thanks. All right, let's wrap this up, guys. So, congratulations to everyone. You guys did an awesome job. Today we went through blockchains and smart contracts. We talked about Ethereum and Solidity, as well as the Oracle problem and Chainlink. Then we talked about some of the Chainlink tools and features. And not only that, but you all created your first smart contracts. You deployed your first smart contracts to a live Ethereum network. You interacted with the smart contracts. You interacted with Chainlink oracles, and you used you used Chainlink price feeds. You did requests for randomness, and you reached out and you did API calls as well. So huge step to take in your journey as a smart contract developer, or in whatever you're trying to achieve out of this. So I know it was a bit of a tight timeline today, but we did a lot. You guys did great, and you should feel very proud of yourselves. And hopefully you're excited for tomorrow. So tomorrow is going to be the final day of this weekend boot camp, and today was really good, but it was kind of just an introduction to kind of get you used to some of the things you do as a smart contract developer in terms of deploying contracts, interacting with them, having to wait for blocks to be mined, funding contracts and things like that. So tomorrow we're going to go out of the shallow end into the deep end, and we're going to work with some other developer environments. And it's going to be lots of fun, and I can't wait. So once again, thank you for attending today's session. Please fill out the feedback forms if you haven't, that'd be great. And we look forward to hopefully seeing you guys tomorrow and continuing on with the boot camp. Cool, thanks all. If you have any questions again, or you're still struggling with an exercise, join the Chainlink Discord. There's a developer bootcamp channel. We'll be monitoring that from now until tomorrow's session, and hopefully we'll try to answer questions. And if you're having trouble with obtaining Link or ETH with the faucets, post your address in that channel, and some stage tomorrow before the session, I'll make sure I'll go through and I'll send everyone some ETH and Link as well. So thanks all.